This second video on complex numbers Loci is looking at a statement like this: argument of z minus z1 equals theta, where z1 is a constant, it's a complex number, and theta is a constant, it's an angle, and z is a variable. And what it gives us is the half line that starts from z1, makes an angle of theta with the real positive axis, or the real positive direction, anti-clockwise. And we can think of it, if we like, if we think of this location as being z1 and this location as being z, then this vector here is the vector from z1 to z is the vector z minus z1. So what we're really saying is that the angle of the vector from z1 to z, from z1 to z, the angle z minus z1, makes an angle of theta. So it gives us a line there. And so you can just remember that. Or if you want to, we can actually get the equation of the line on which z lies. Although remember that the Cartesian equation will give us the whole line, whereas what we actually want is the half line. Okay, so how we get the Cartesian equation is that we let the variable z equal x plus I, y, so that then we are converting the real axis to an x-axis and the imaginary axis to a y-axis. And that now means that the argument of z plus 1 plus 2i becomes x plus I, y plus 1 plus 2i equals pi over 3, which means that the argument of x plus 1, which is the real part, plus y plus 2i equals pi over 3. And then the next thing we need to realize is that in general, if we have a complex number z being a plus bi, and we think of a plus bi as being like this, where this part is a and this part is b, then the angle and the argument of z is theta, so there's theta there, then tan of the argument of z, which is tan of theta, will be b over a. So in general, tan of the argument of a complex number is the imaginary part, b, over the real part, a. Okay. Now, you might try to use this to work out what the argument is by doing the argument of z equals tan to the minus 1 of b over a. But remember, there's more than one angle for which tan of the tan of the angle will give us argument of z. And so you have to be careful when working out the argument. But you can use b over a, and from that work out which quadrant it's in, and then work out if it's negative, we need to add on pi or whatever it may be. Okay, so in this case, we've got a complex number, and here we are. So we've got this complex number, x plus 1, real part, y plus 2, the imaginary part, and the argument is pi over 3. So if we take tan of this, it basically means that tan of pi over 3 is going to be the imaginary part over the real part, and tan of pi over 3 is tan of 60 is root 3, and so that's going to be y plus 2, the imaginary part, over x plus 1, the real part, and so we get y plus 2 equals root 3 x plus 1. And what is this? This is the equation of the line through minus 1, minus 2, with gradient, that was a 3, with gradient root 3, which is consistent with what we see with the equation here, that it starts at minus 1 minus 2i and goes at an angle of pi over 3, which means that the gradient is root 3. So that's one question. Let's have a go at another question, and that is where we have an inequality and we have the argument of z plus 1 plus 2i, instead of being equal to pi over 3, we have that it's less than or equal to pi over 3. Now remember that in general, an argument of a complex number is given as an angle from pi down to minus, a strict inequality at the bottom, I should mean, minus pi. So in other words, if we're measuring an argument, then it can be anything from 0 round to pi, and it can be, or from 0 round to minus pi, and we include pi but not minus pi. Okay, so here if we want to get this, we can see that just like before, we are interested in the point minus 1 minus 2i, and the angle of pi is going to be in this direction, and that's, or pi over 3 rather, and we want the argument to be less than pi over 3, but because the argument has a minimum of minus pi, then we have that actually what this means is that the argument of z plus 1 plus 2i is actually going to be up to pi over 3, but the lowest value it can be is minus pi. Okay, so an argument of minus pi will be around to here, that's minus pi, and there is pi over 3. So we're going to want to include all of this area here, not including the line where the argument is minus pi, but including the line where the argument is pi over 3, and not including the point minus 1 minus 2i. Okay, so I hope that helps. I'm going to do a last example, which is example 3. And this is taken from integral. So the argument of z minus 2 minus I. We want to look at it when the argument is greater than 3 pi over 4. Oops. 3 pi over 4. Now remembering that the argument can have a maximum of pi, what that basically means is that the argument is going to be the argument of z minus the complex number 2 plus 1i, and it's going to be at least or more than 3 pi over 4, but the biggest it can be is pi. So in practice that's what we're going to have. So if you think of the complex number with coefficients 2 plus I, then the argument, it needs to be at least 3 pi over 4. So if we take the horizontal direction and measure our angle, pi over 2 is vertically, 3 pi over 4 will be at angle 45 degrees, or pi over 4 to the vertical. So it will be in this direction, and I'll do a dotted line because I don't want to include that line. And this angle there is 3 pi over 4. So it's at least that. And the maximum it can be is pi. So I will include that line because that makes an angle of pi in total. And so the region for which the argument of z minus 2 plus I is between 3 pi over 4 and pi, excluding 3 pi over 4, but including pi, will be this area here that I'm shading in, where the ray coming from 2 plus I at an angle of 3 pi over 4 is not included in the region, but the ray making an angle of pi with 2 plus I is included. Okay, well, I hope you understand that, and that's okay. That's the end of that video. If we can just quickly close this.